Now we're going to look at continuous functions. These are functions whose graphs have no holes and no breaks. Why would we want to look at this? Well, these turn out to be the functions that are very often used in calculus and its applications. So we want to know them in great detail. And we'll start out with the very beginning definition, functions continuous or not at a single point, which we'll call C for the moment. All right, let us state the question that we're interested in answering here. The question would be, what properties of a function cause what I referred to earlier as breaks or holes in its graph? Another way to say that is, so it, meaning the function, does not continue. Doesn't continue past the break or past the hole. We want to know, if you start with a function, what properties might that have before we even look at the picture that will determine whether or not its graph has a hole in it. And we'll find out what those are, and then we'll try to define a way. We'll find a way to define the function so that we can define away those problems. So let us go ahead and start with an example so we can see what we're up against. Consider the following function. Now, this function is made up for the purpose of illustrating all the different kinds of things that can go wrong. So we'll start here. We'll just put 1 and 2 on the vertical axis, and we'll mark 4 values here on the horizontal axis. And let me draw the function as follows. It has a point at 1. It comes down here to 1 on the, it has a point at x equals 0, which is the y value of 1. Down here at 1, it has no value. Up here, it goes straight across. Then the value at 2 is actually up here. And at 3, we'll assume it has an asymptote so that the graph can look something like this. And then we'll put an open hole above 4 and continue the function off this way. So this function has breaks in it of all sorts. Let's see if we can talk about each one of them and what kind of break they might be. This first one here, you can see if you're starting from the left and you're coming down to the function and then you have to hop up here to continue, there is a break there. And it looks like a jump, so that is in fact what it's called. What happens here that makes that jump happen is that no limit exists as x is approaching 1. And when I write x approaches 1, I mean x approaches 1 from either side. It's a two-sided limit. So in this case, you can see what the problem is. If you approach from the left, the limit seems to be taking you down to a height of 0. If you approach from the right, the limit seems to be taking you to 1. So there is no two-sided limit, and that seems to explain why there's a jump in this function. And I'll even write the word jump here. Let's move over to what's happening here at x equals 2. In this case, apparently the limit from both sides is heading toward this value where there's a hole, so that doesn't seem to be the issue. What seems to be the issue is that the actual value of the function, the dot above 2, seems to be out of place. We'd love to have it here so that we'd have a continuous function, but in this picture it is out of place. That seems to be the issue here. So let's go ahead and write that down. The limit at x equal 2 exists, but is not equal to the functional value at 2, which is higher. It is at this point. Now let's look at this asymptote. We can see the function from either side is heading downward, and it is heading downward to apparently negative infinity, which means there is no limit because negative infinity is not a real number. This is no limit, exists as x approaches 3, and again, that's from either side. Finally, let's look at what's happening here at 4. At 4, notice there's no value of the function anywhere above 4. There's just this hole, so that means the function is not defined there. So I'd say f of 4 is not defined. So we've seen all kinds of difficulties here in making this particular function very discontinuous. It has a jump here. It has a point defined here but out of place, so it's a single point issue. Here the function blows down to infinity, as we said before. And here the function has a hole that's not filled and not fillable. There's actually no value of the function there. So we seem to have looked at all the different things that can go wrong. So with this in mind, I think we can write down a definition that should cover all of those cases. So here's the definition. A function f is so-called continuous. That's the word being defined at the point x equals c. So we're talking about continuous at x equals c, a given point, provided all three of the following conditions are met. So all three conditions are satisfied. And we need them all to avoid all the difficulties we just saw. First of all, we certainly want the function f at c to be defined. If there is no functional value, then there's an automatic hole and the function won't be continuous there. Another way to say this is to say f exists at x equals c. The second point that we noted in a couple of the examples is that if you take the limit of f of x as x approaches c, double-sided limit, that limit must exist. If it doesn't, we saw in the first case that we'd get a jump, and that would be a case where the function's not continuous. Now exists also, just to strengthen that statement, must equal a real number. That avoids the entire issue of the function going off to negative infinity, as we saw. Finally, the last case is that both the limit and the functional value must equal one another. That would be the case where we had the functional value defined and the limit defined, but the functional value was too high. It was in the wrong place. It was out of place, as I said. So we'd want those to be equal. That seems to be sufficient, and this is often referred to as the three-part definition of continuity. And it's actually continuity at a point, in this case the point C. So these are the three things you must check if you want to know whether a function is continuous at a given point. And say you don't have the graph to look at, or the graph is not going to be drawn until you figure this out. These are the three things that must be fulfilled. The function must exist at the point in question, the double-sided limit, two-sided limit must exist there, and both those two items must be equal. That is what will make the function continuous, and if not, if you do not meet these conditions, then what we say f is discontinuous. Discontinuous. So sometimes we say not continuous, but discontinuous is more common, at x equals c. Now, let's look at an example so we can see how all of this comes into play. So here's a nice example. And this will be one where we actually have a formula for the function. So x squared minus 4 over x minus 2 is our function. Now this is a classic. It has lots of nice features that we're going to want to discuss. So let's notice a few things. Notice that f of 2, the value of this function at 2, does not exist. Why? Because if 2 is put in for x, you're dividing by 0. And you can't do that. That doesn't make any sense. So f of 2 does not exist, or is undefined if you like, and the reason is division by 0, which we always have to watch out for in any expression that has a quotient. All right. For x's that are not equal to 2, 2 is the problem point, for x's that are not equal to 2, f of 2, observe, or f of x rather, for x is not equal to 2, which is x squared minus 4 over x minus 2, you may have already noticed that the top is a difference of two squares and hence factors. So I could write x plus 2 times x minus 2 over x minus 2. And the only reason I'm now going to be able to replace the x minus 2 over x minus 2 by 1 is that x is not equal to 2. So there's no danger of doing a 0 by 0 argument. So this, in fact, is just x plus 2. That's going to be true for x not equal to 2. So this function's graph is going to be just the graph of the simple line x plus 2 everywhere, except at that one problem point x equals 2. So let's write that down just to get it on paper here. So f of x is x plus 2 everywhere, except at x equals 2. Now that tells us a lot of information, so let's go ahead and do a graph. So over here we can draw this, and let's mark 2 here. 2 is the place we're interested in. And then we'll go up 2 here, and this would be then the graph passing through 4 of our function, which is x plus 2. So it's the x line, which is the 45-degree line, shifted up by 2. This is our function f of x. And this is the graph we would have for this function that we started with. Now, suppose we wanted to modify this function so that this function would become continuous. Well, we'd have to change it, of course. What we'd like to do is find a value that will fit in this hole exactly. So if I didn't do that correctly, I could create a new function which would look exactly the same as this one, except in one instance. So let me first draw it as much like the other one as I can here. We're going to call this function g of x, and we will put a value here. That's the new value, so that g of 2 will be equal to 3. So g of x looks exactly like f of x everywhere else. At this point, however, it's got a value of 3, which the original f of x did not. Now, both of these pictures show you a discontinuous function. But they're discontinuous for different reasons. In the first case, it's discontinuous because the function's simply not defined there. Here, the function is defined there, but again, the point is out of place. So that's a kind of discontinuity. If I were to redraw this and create a new function where I took h of 2 to be, well, what height should that be? It looks like it should be 4, right? If I made h of 2 equal to 4, then this would be a continuous function. Continuous at x equal 2. So I can sometimes start with a function that has a single flaw and replace it with a function like this h function, which would fill this dot in here with the point required to make the function continuous. And this is what you'll be faced with in problems very often. So, for example, one could ask in a problem, which will be very commonly done, something like this, say. Where is this function, and it will be written this way without a picture, x squared minus 4 over x minus 2. That will be true for x not equal to 2, and it will be equal to 3 for x equal to 2. Where is that function continuous? So if we look at the picture from the previous page, that is the center picture here, and you see that if you draw the picture, you'll see immediately that the function is discontinuous at 2. And then we'll want to find out how to prove that this is discontinuous, because we don't want to only just look at a picture. And what we'll have to do is examine the two-sided limit at 2. And I'll be doing examples of that coming up. But before I leave this, let me remind you one more time that a function continuous at a point x equals c must, as our definition says, must have a two-sided limit. A two-sided limit there. Now this will have bearing later, so let's stop there and we'll come back in a minute. Now that we've seen the basic definition of a continuous function at a single point, we want to move on to larger sets of points. And some of the sets that we look at most often are, of course, intervals, open intervals and closed intervals. So let's look at functions continuous on an interval. Well, first let's deal with the open interval case because that's the easier of the two. And we'll just say f is continuous, and we use the word on now. It's continuous on an open interval a, b, or the ultimate open interval, which is an entire set of real numbers, minus infinity and infinity. So continuous on either one of those intervals. And let me draw a picture of them to make sure we're clear on what we're talking about. Here might be a picture of AB, and there might be an arbitrary point in AB. And of course, the real numbers is the entire line, and maybe there's an arbitrary point C. F is continuous on these open intervals, as you might expect if it's continuous on all the points in those open intervals. So if f is continuous at each individual x equals c value in the interval in question, in this case, these open intervals. Now, the point here is that two-sided limits are possible here. Because you're in an open interval, we can approach any point at an open interval from either side. So two-sided limits are possible here at each one of these x equals c. Now, that takes care of all the open intervals we'll ever see. What about closed intervals, or even intervals that are closed at one end or the other in any of these cases? So, what do we do in that case? What about f defined on, say, a closed interval AB? Now, this will extend to the case where it's only closed at one end or the other, but if we do both of them, we'll see how this works. Now, the problem here is that there are no two-sided limits at the endpoints, no two-sided limits at A or at B. So our definition for continuity, which involved two-sided limits, fails at these two endpoints. We cannot take a limit, for example, at A as we come from the left because the function's not defined there. It's only defined on the interval. So we could only take a right-hand limit at A, just like we could only take a left-hand limit at B because we can't come from the right. There's no function out here. So the end result is we need a new definition. Luckily, we have an easy way to handle it. We've already defined one-sided limits, so we're going to pull them out and we'll be able to define what we need. So at x equals c, we will say f is continuous from the left. So from the left is what's being defined here, continuous from the left, if when we take the limit of f of x as x approaches that point c from the left, and that's our notation for coming from the left, if we get f of c, then we will say the function is continuous from the left. If you want a picture of that, you can have a picture something like this. If this is your c point, then if you come from the left towards c, then the function will be defined like that, and not defined on the right necessarily. Continuing, we can go ahead and say at x equals c, f is continuous from the right if, well, you can guess this now, if the limit of f of x as x approaches c from the right, that's c with the plus in the superscript position, if that equals f of c. So in this case, if this were c here, then we would have perhaps a picture like this. We'd approach c from the right, and the function would be defined up to that point there. So, with that in mind, having from the left and from the right continuity defined, we can go ahead and define continuity on a closed interval. F is continuous on the entire closed interval, AB, if, well, F is continuous on all the interior parts, if it's continuous on the open interval f is continuous from the right at, well, let's see. If we're at A, the only way we can approach A is from the right, so that must be A. And finally, f is continuous from the left at B, because in the closed interval we can only approach B from the left because we have to approach on a side where the function is defined. So that defines continuity for functions on all the intervals we'll see. And it is just as simple as that. Now that we've seen the definitions of continuous functions on sets as large as intervals, let's start asking ourselves some questions about the properties of continuous functions. What happens, for example, if you add two continuous functions? Is the result a continuous function? And other combinations that might occur. So, let us look at properties and combinations of continuous functions and get the basic facts. So we'll start, recall. And this is something very familiar from what we did before, but we'll put it in the context of continuous functions now. If you have, say, a p of x, which is a polynomial function, very familiar functions that you'll see a lot of in this course. If p of x is a polynomial function, then if you take the limit of p of x as x approaches c, two-sided limit, and c is any real number, you always get p of c. We talked about this before when we were doing limits, that when you take the limit of a polynomial function, it is exactly the same operation as simply substituting the c in for the x. Now, in this context here, that means that this particular kind of function, so we can conclude the following: every polynomial function is continuous everywhere. That's what this means in this context. I'll even box that in. Every polynomial function is continuous everywhere. And you should know this from your experience. If you start with a simple polynomial function like a line, you know that it's continuous everywhere. It has no holes or breaks. The same thing with a parabola or a cubic curve or a quartic or any of the other polynomials you've seen. So, with that in mind, let's go ahead and go a little further. Suppose we're given two functions, say, and call them f and g, and we'll suppose that they are continuous at the same point, x equals c. Then the theorem that I can write now is the one that you would hope is true, that first of all, if you take f plus g and get a new function, which is the addition of these two, the sum of those two, or if you take the difference of two functions, or if you take f times g, all of these are all also continuous at that same point. Now I'm going to omit the proofs for these, although we'll talk about how to check for continuity later. But now you know that if you start with two continuous functions, you add, subtract, or multiply them, you will end up with a continuous function. That's very nice. The property of continuity is not lost. Now there's one operation left out here, and it's the usual problem operation. If I take f over g and form the quotient of those two functions, then this is continuous at c only under certain conditions. F over g is continuous at x equals c, provided g at c is not equal to 0. We cannot divide by 0, and that's all that we're avoiding here. Otherwise, we can write this down just to have it in one place. Otherwise, f over g is what we've started calling discontinuous at that point x equals c. So that takes care of all of the arithmetic operations, the addition, subtraction, multiplication, and the division of two functions. We will then, in a moment, get back to the other kind of operation, which is only applicable to functions, known as composition. But before we do that, let's see if we can extend what we have here to some familiar cases. Immediately we can say the following, and add this to our collection of well-known facts. Every rational function, and a rational function, remember, is simply the quotient of a polynomial over a polynomial. Every rational function is continuous at every point where, well, let's see, where the bottom is not 0. Of course, it's a quotient. That is the only issue with a rational function. Find out where the denominator, or the bottom, is 0, and you've discovered where the function is discontinuous. Let's look at an example. Consider this function, f of x equals x squared minus 9 over x squared minus 5x plus 6. And we'll ask the question, where is f continuous? Now that may sound like a harder question than it is, because you're thinking, I have to check all the various points where this function might be continuous. But in fact, you don't have to, do you? It's a rational function. You know that you have a polynomial on the top and a polynomial on the bottom. The only place where this won't be continuous is where the bottom goes to 0. So that's all you have to check. So that's exactly what we'll do. We want to solve, in order to find out where it's 0, x squared minus 5x plus 6 is equal to 0. So with just a little bit of effort, we see that this factors so that x is equal to 2 or x is equal to 3. These then are the points where f is not continuous, or if you like, discontinuous. Everywhere else, f is continuous. So, let us look at, to continue our analysis here, let's look at the following handy fact about a very familiar function that you see a lot of in this course, the absolute value function. The absolute value function is continuous everywhere. Now, rather than just say that, this is a perfect opportunity for us to check this fact using the definition of continuity that we have. So let's go ahead and check that. Proof. Well, let's first recall we can rewrite this function in a way that clarifies its various parts. It is x if x is greater than 0. It is 0 if x equals 0. And it is minus x if x is less than 0. Now, we can argue that we know about its continuity almost everywhere. Since both x, the top, and minus x, the bottom here, are just very simple examples of polynomials, we know that f is continuous everywhere except possibly at x equals 0, the one place we haven't checked. So this is the point we're going to check now. And what we will do is we'll set up what we're going to do, and then we'll go ahead and do it. We check the three-part definition of continuity at the point x equals 0. And that's what we're going to do on this second page. So the first question we have to ask is, does the functional value at 0 exist? That's the first question. Well, the answer is yes, because f of 0, which is the absolute value of 0, is in fact 0. All right. 2. does the double-sided limit as x approaches 0 from either side exist? Because we learned that that was essential. Well, in this case, bringing back the definition here, we see that the function is defined differently on either side of 0, so I'm going to have to check the two one-sided limits and see if they equal the same thing to see if there is a two-sided limit here. So that's what I will do now. Let us first look at the limit of f of x as x approaches 0 from the left. So that's the limit of, if you come from the left, the function is actually minus x as x approaches 0 from the left, and that is just 0. And then the other one-sided limit as x approaches 0 from the right, that will be the limit of just x, because the function is just x in that direction. And again, I get 0. So the answer here is yes. The two one-sided limits exist, therefore the two-sided limits exist. Two-sided limit exists because these two one-sided limits are the same. All right, finally, we ask the question, are they equal? They meaning the functional value at 0 and this two-sided limit. Well, the first one is 0 and the second one is 0 also. So the answer is yes. So what do we conclude? Let's just write it out. So the function f of x equals the absolute value of x is continuous at 0, 2. And since it was continuous everywhere else, it is now continuous everywhere, as we were trying to do. Finally, in this section, lastly, I did mention before that there was an operation that we hadn't looked at for functions, the operation of composition of two functions. And the fact about composition is, and it's a nice colloquial way of saying this, the composition of continuous functions is also continuous. So not only can you add, subtract, multiply, and divide functions and get continuous functions under the right circumstances, if you take and compose one function with another and they're both continuous, the end result is also continuous. So let me write out the theorem and then show you a picture to illustrate it. You need to, in calculus, as in higher mathematics courses, you need to learn how to read these theorems and make sense out of them. It's very important in calculus that you draw pictures, all of the time to illustrate the ideas involved. If you do that, you'll learn your calculus at a much deeper level. Here is the theorem here, and then we'll look at the picture to see what it means. If G is continuous at C, and F is continuous at G of C, because in this composition we're going to assume that G goes first, F goes second, and we'll see that in the picture, then F composed with G, with the composition notation there, is continuous at C. Now, if you look at the picture that illustrates the composition of these two functions, you'll see what happens. If you start with C and you first apply G to it, you end up, of course, with G of C. If you next apply F to it, you end up with F of G of C. And if you call that entire operation a single function, that's what we call F composed with G. G on the right is the first thing that's done, and then F follows. This is the composition, and what this theorem says is, if these two pieces are both continuous, then the entire function is continuous. The composition is continuous. For example, here's a case where we will use this immediately. We often take the absolute value, so we often take the absolute value of a continuous function. Well, the absolute value, as we just showed, is continuous everywhere. The continuous function, of course, is continuous. The composition of the two, that is to say the absolute value of the continuous function, is also continuous. And that follows from this theorem. So you see, we will be using this theorem very often when we make compositions of functions. And one of the most familiar, of course, is the absolute value of a given function. So with that, we'll leave continuity now for the moment. Now I'll examine a property of continuous functions that is useful in the solution of equations. And this will be the intermediate value theorem, which will state that property. And what we'll do with that is we'll be able to approximate the roots or the solutions of equations like f of x equals 0. So, without further ado, let me go ahead and write down the intermediate value theorem. And as I said before, it's good practice to learn to read these and see if you can extract the meaning. And one way to do that is to draw pictures to illustrate what is being said. So I will write this first, and then I'll draw a picture to illustrate it. So here's the intermediate value theorem. Suppose, or start the theorem as with an if statement, if f is continuous on a closed interval ab, and, second hypothesis, k is some real number. K is between f of a and f of b. Now, I don't know which one of these will be bigger, so I'm just saying between to save myself the trouble of writing out the two different cases. So we'll suppose we have a number that is, if you like, a y value between the f of a and f of b value, wherever they are. Or it could be equal to one of them, or equal to one of them. Then, under those conditions, there is at least one value of x in that closed interval ab such that f of x is k. So there actually is a value of the function at that height k. And remember that height k was any number that was chosen between f of a and f of b. Now, why would that seem reasonable? Well, let's look at a picture, and we should be able to convince ourselves. So here is the idea. Let us start with the picture as the theorem outlines. We have some sort of continuous function here. So here is f, and it is continuous on that given closed interval ab. Now, remember what that means? One way of saying that is that it has no holes in its graph. So let me mark a point A here, and some point over here for B. And this is the x-axis, and this is the y-axis. Now, the theorem refers to f of a and f of b, so let me mark those also. Here's a. This, then, is the height f of a. And here's b, so this must be the height f of b. And the theorem says pick a number between f of a and f of b. Now, in my picture, f of a happens to be the bigger one. But it doesn't matter. I'm picking something in between. So maybe I'll pick a point here, k. And I'll write down here, pick any k here. Now, that k value comes over this way. And what the theorem says is, it says there's got to be a point on the curve. Another way to say that is, this point here has to come from some x value down here. So that x goes up to here, and if it's on the function, the height is f of x, so f of x must equal k. So the k yields the x. And the theorem says there must be an x with f of x equal our height k. And the reason is the graph has no holes. No matter what k you choose here, if you run across here to the graph, you have to strike the graph. The graph has no holes in it. So that means there has to be an x down here whose height, f of x, is equal to k. That is the reason the intermediate value theorem is true. And that is the reason that you draw pictures in this course, so that you can see these ideas clearly. Now, that may seem like a completely obvious property of continuous functions. Let us go ahead and show you an application that shows that this obvious property can be very useful. Here's a nice application. Let us suppose we have this particular situation. Again, those are my two axes, my x-axis and my y-axis. Suppose in this case the function looks something like this. So that here would be a, here would be b. This would be the function, which remember is taken to be continuous. And now let us show, well, let me first mark in that this is f of a, there's a height here. This is b, so the height here would be f of b. And this time let me take k to be 0. K is a height, remember, so the 0 height would be right here on the x-axis. Now notice that k is between f of a and f of b, because f of a happens to be above 0, positive number, and f of b happens to be below 0. So this is above 0, and this is below 0. And k is in between. Now, if I follow what the theorem says, it says there has to be an x value along here whose height will be k. In other words, an f of x, a value such that f of x equals a height of 0. That means this point here has to exist. And x must exist with f of x equal to the height k, and the height k is 0. But if you look at that in another point of view, you see that what we've done is we found a solution to this equation. We found an x value that makes this true. So the theorem one can write from this, and it really is just a corollary of the previous theorem, is if you have this situation, you find at least one root. So what is this situation? If f is continuous on AB, and f of A, f of B are non-zero. See, in this picture, one's definitely above 0, one's definitely below. They're non-zero and with opposite signs, as the picture also illustrates. So one is below and one is above, one is positive, one is negative. Then there is at least one so-called solution, if you like. Solution of the equation f of x equals 0 in the open interval AB. And it's open because we've eliminated the possibility that f of a or f of b would be solutions by saying that we wanted them to be non-zero. So this is a way of finding a solution. This guarantees that there's a solution. All you have to do is take your continuous function and show that there's a value of the function somewhere that has, say, a positive value and one that has a negative value. There must therefore be in between one that has 0 value. Let's illustrate this with a particular example. And it would be phrased something like this. Solve for x. X cubed minus x minus 1 equals 0. Now, you might think this is just an algebra problem, and what is it doing in this calculus course? Well, first of all, yes, it is an algebra problem. But if you think about it, you probably don't have much in the way of technique for solving a cubic of this kind. And so what do we do in that case? Well, first of all, let's just acknowledge that the algebra is not easy. And the second point is, how do I even know there's a solution? I would like to not have to waste my time if there's actually no solution. I'm going to guarantee that there's a solution by using the intermediate value theorem as we just did. So we could write the question and then answer it. Does a solution exist? Okay, well, let's see what we have here. This function here on the left, we could write as, say, the function p of x equals x cubed minus x minus 1. Now we have a function that that previous theorem will apply to. Is that function continuous? Sure it is. Is it continuous, as it turns out, everywhere? Yes, it's a polynomial. So p is continuous everywhere. So it's going to be continuous on any particular closed interval I want to look at. Now, let's do a little trial and error, because this is really the fastest way to do this. By trial and error, or you can go ahead and look at a graph. If you have a grapher, such as a graphing calculator, you can produce a graph of this. And then you can observe that, say, and this is just an arbitrary choice that works, p of 1 is 1 minus 1 minus 1, which is minus 1. And p of 2 happens to be 8 minus 2 minus 1, which is 5. And notice that these are non-zero, and they have opposite signs. So by the previous theorem, there must be, between 1 and 2, an x value that makes this particular polynomial equal to 0. So, by the theorem, for some x in, and the interval is determined by these two endpoints here, in the interval 1, 2, p of x is equal to 0. So the answer to the question, does a solution exist, is yes, there is a solution. Now, the practical man would now say, well, so what if there's a solution? How do I get an estimate of what it is? If I can't find it exactly, which I probably can't in this case, how would I at least approximate this solution? Well, we won't spend much time on this right now, though approximation ideas are very much part of the development of calculus coming up. But we can say a couple of things about this. To approximate a solution, you can either, and this sounds like there are only two ways. There are actually many ways, but these are fairly simple ways. You can either say, systematically, guess values in 0 and in 1, 2 rather, and check them. Every time you get two values that are of different signs, if you get an f of a and an f of b that are, one is positive, one is negative, then you know that there is a solution in between those 2 points on the x-axis. And you can, if you can narrow this down, you can continue to find better and better approximations to what that solution is. Or another way to do it even more efficiently is you can use the zoom in function on a calculator or on a grapher, which is a piece of computer software. So you can zoom in with a grapher, or you can check various values, but either way you can find better and better approximations. But the point of all of this example, of course, was to illustrate how you can show that there is a solution to be found in the first place using the intermediate value theorem. And with that, we'll pause and come back and do some exercises. Now, as I said, let's look at some exercises. The first one I will start you off with is the following. Find k, some real number k, such that the function defined by, piecewise defined, 7x minus 2 for x less than or equal to 1, and k times x squared for x greater than 1. Find a k such that that function is continuous everywhere. So that's your task. Why don't you give it a try? let's see what kind of solution we can come up with. First of all, by looking at this a little carefully, 7x minus 2 is a polynomial. Kx squared, whatever k is again a polynomial. So these two pieces are polynomials, and I already know polynomials are continuous everywhere. So the only possible place where this piecewise defined function might not be continuous is where x equals 1, which is the break point between them. So I only have to check one point. We need only check at x equal 1. So that's the only point we'll look at. Now, to check continuity at a given point, we need to check the three-part continuity test. So let's take it one by one. Note that if we evaluate the function at 1, let's see, 1 is part of the top, so that means I'd use this form. So that's 7 times 1 minus 2, which is 5. That certainly exists. So I've established the very first part of the three-part continuity test, that the functional value exists there. Now, we want to then check that the two-sided limit exists too. So to check that the two-sided limit exists, because it's piecewise defined, in these cases you will almost always have to check the two one-sided limits and then see if they equal the same number. So to check that the two-sided limit exists, we check the two one-sided limits. So let's just go ahead and do that. So we take the limit of f of x as x approaches 1 from the left. Now that limit as x approaches 1 from the left is determined by the function which is defined to the left as 7x minus 2. That's just a polynomial, so we just need to put the 1 in. 7 minus 2 is 5. Then the second one-sided limit is where we approach x approaches 1 from the right. So that is the limit as x approaches 1 from the right of, we come from the right, the function is kx squared. So it's k times x squared. Putting the 1 in for x, we end up with k. So for these two to be equal, we must have k equal 5. And if they are equal, and they are equal to 5, notice that the functional value was 5, so that all three of these are equal to 5, and the function is then continuous at that point. So we found the answer to our question, which is that k must equal 5 here. And that's all there is to this particular example. So I hope your work was similar to that. Let's look at another one. Where, in this case, where is this following function f not continuous? Not continuous. I was going to write discontinuous there. Not continuous. And is it repairable? So we'll find out where this function's not continuous, and we'll ask the question, is it repairable? Could I alter the definition of the function easily so that the new function would be continuous? So let's take f of x to be x squared plus 3x over x plus 3. Now you go ahead and try that and see if you can show where it's not continuous, and then answer the question of whether or not we might be able to repair it. Let's see what my solution would be. Where is f not continuous? Well, first of all, this is a rational function, polynomial over a polynomial. These functions are going to be continuous everywhere except where the denominator is 0. So I know immediately f is not continuous at x equals minus 3, because that would make the bottom 0, and division by 0 is not defined. Now, I'd like to know what the function is doing everywhere else so that I can see if it's repairable. Let me observe the following algebraic fact. For x not equal to the problem point minus 3, notice that if I write the function out, that the top has an x common, so if I factor that out, I have x times x plus 3 over x plus 3. Because x is not equal to minus 3, as I've said here, the x plus 3 is not 0, so I can actually write x plus 3 over x plus 3 as 1, so this becomes x, which means our function, f of x, is just the plain function x, as long as x is not equal to minus 3. Well, that's handy. Let me see what that picture looks like. So I'm going to find the problem point first, minus 3, which would be right there. Then otherwise the function is just the x function. So this is f of x. And this is the picture of the function, and I can see it's not continuous here because it's not defined here. Now, I can also see that because there's only a single hole of discontinuity, this ought to be repairable. So, in answer to the question, is this repairable? I'm going to say yes. And then, of course, I'm going to show you how to repair it. So I would say, let us go ahead and define a new function, which will be equal to f of x, where x is not equal to minus 3. So that's all of this line, except this hole. And then where x is equal to minus 3, what would be required to fill in this hole? Well, ideally, this function would be just x. So if x is minus 3, then, well, x is minus 3. So g of x would have to be minus 3. In that case, we'd have a function which is repaired. It is a version of the original function with a minimal repair. We have simply filled the hole where the original function was discontinuous. Now later you may learn that this kind of a discontinuity is called a removable discontinuity, and that's because it is repairable. All right, let us go ahead and look at one more example. And it is the same question as before. Where is f? And I'll go ahead and write discontinuous this time, just for a change of pace. Where is f discontinuous, and again, is it repairable? Okay, and the function is f of x. Again, piecewise defined, 2x minus 3 for x less than or equal to 2, and x squared for x greater than 2. So go ahead and look at that, and we'll be back in just a moment. Now in this case, I am going to resort to my usual technique. Whenever you have the chance, draw something, because the visual image probably will enlighten you about the problem. Since I have this piecewise defined function, I'd really like to get a picture of it to give me a sense of where this function might be discontinuous. Now as before, 2x minus 3 is a polynomial, as is x squared, so the only place where this function might be discontinuous is at the place where these two might meet, which would be at x equal 2. So let me go ahead and draw my picture here. So x equal 2 is going to be the interesting point. Let me first find what happens to the top function as x equals 2, because it's defined there for 2. Well, when x is 2 here, it's 4 minus 3, it's at a height of 1. So the function has a value 1 there. And let's see, when x is 0, it's minus 3. I only mention that so that I'll have another point so that I can draw the line. So the function to the left of 2 looks like this. To the right of 2, it's just the familiar x squared function. If x were equal to 2, this would be 4. So I know that I need to look up here at 4. The function is not defined at 4. It's x greater than 2 after all. And then it's just going to be the parabola going off to the right. Now, when I look at this, I see immediately that the function's discontinuous at 2. It has a jump of 3 units. Now, I want to verify this. So let me write this down. F is not continuous at x equals 2. That would be by looking at the picture. Now, when you're learning mathematics and you're learning calculus in particular, you want to be able to not only judge or draw conclusions from a picture, but you want to also be able to draw conclusions and write down what the picture is representing. So it's a two-part process. You want to be as mathematically symbolic as you can and have the visual image to back it up. So in this case, I can see what's going wrong. I can see that the two-sided limit at 2 does not exist because the one-sided limit from the right apparently goes to 4 and the one-sided limit from the left apparently goes to 1. And I can just write that down. And I can say the limit of f of x as x approaches 2 does not exist because, and I can go ahead and write it down, the limit of f of x as x approaches 2 from the left is the limit of f of x as x approaches, the limit of, well, if x is approaching 2 from the left, it's actually 2x minus 3. So I can actually write that in as x approaches 2 from the left. And as we approach 2, this is a polynomial, so 4 minus 3 is going to give me 1, which is what I saw here in the picture. While, if I take the limit of f of x as x approaches 2 from the right, let's see if I can get this one right, the limit of x squared, there we are, as x approaches 2 from the right. And if I put the 2 in here, I get 4. So I now have symbolically shown that the two-sided limit cannot exist because the two one-sided limits are different. And that is verified by the picture. So I have two ways of looking at the same question, and I've answered it. The two-sided limit does not exist. That explains why it's not continuous at x equals 2. That also answers this question about whether it's repairable. To repair this function would require enormous surgery. This function cannot be repaired by simply altering a simple point. We'd have to find some way to connect these up, and this is just too far. So the answer to the question about repairable, no, it is not repairable. And this discontinuity is called a jump discontinuity, as I've mentioned before, as opposed to the last one, which was called a removable discontinuity because it could be removed or repaired. So with that, we'll stop and move on to another section.